Hello everyone, in this video I'm going to be designing a better PID controller for this thing. So I have a linear actuator, and I also have here a slightly different servo with a gearbox, and I'm going to be cleaning up my PID controllers. Alright, so I have a few things I want to clean up here. So I have the motion profile. I'm going to move this here. This would be the data that is sent from the motor drive or CAN bus to the master. It's the same firmware running on both the master and the slave. So it's two different. It's two cards that are the same card, but they're doing different functionality. Let's see. Control mode. Keep that as it is. And I'm also going to add the filters here as well. Let's see. I'm going to be using second order Butterworth filters, which are very easy to design using MATLAB. So FB filter is going to have float A. These are the coefficients of the filter. B. A is for the previous outputs, and B is for previous inputs. So it's going to be a finite response filter. I guess that's pretty much it. Let's see. Actually, we can do like this. So I'll have a filter for the derivative. That will be the derivative of the error. I'm going to be using derivative and error instead of derivative and value because that's just easier to simulate in MATLAB. But it's there is an equivalent form of PID controller where you just use the derivative on value, but then you have to switch the sign in front of the derivative. And it basically has the same effect, except that it's not sensitive to set point changes as much as the derivative and error version is, which is the standard version, by the way, the derivative and error. That's the typical PID controller that you see in any, like in 95% of cases. So let's see. I also need a filter for the state. This is one huge structure. I'm thinking I would need to, I need a filter for the position and the velocity for both pitch and yaw. Or at least for pitch, because the pitch is an ADC input, while the yaw is an encoder, so the yaw is much more precise. It doesn't actually need a filter, I think, but pitch does need a filter. I'm just thinking if I should have a state that's a more generic state, where I estimate the velocity and the filtered position, or to have that in the controller. I think that I'm going to have a generic state. So this is the place where I plan a trajectory when doing the automatic move. When I do a manual move, I just dynamically update the position and based on the commanded velocity. So the potentiometers regulate the maximum velocity and acceleration. But when doing an automatic move, it is necessary to plan the trajectory so that you get kind of like an S-curve. And you also get the velocity and acceleration set points. And currently I'm not using the acceleration set point because I'm not currently controlling the current, but that's something I'm going to add as well. So I'm gonna update this also. This is the acceleration set point that is set using potentiometers. This is not the actual acceleration. It's just kind of like a set point. So I'm gonna update this here. this maps the ADC values to appropriate range in as a floating point value. So this will be FB max pitch hack and this shouldn't be 0. This should be like some kind of because you don't want to have the acceleration set to 0. Then nothing is going to move if it's set to 0. So it has to be some small value as a minimum, and the maximum will be just, let's see, yeah, and the maximum will be FB max pitch. Alright. Damn it. It's actually pitch max. Yes, pitch max acceleration. Okay. That didn't work. Let's see. Like this. Yo, max. Snare. And then this can be removed. So, a small simplification. And then for the pitch, I plan the trajectory from the current pitch position, which is going to be the position of this linear actuator, and the 0 point is in the middle. Then there's -1 and +1. But for the other servo, it's actually a position in radians. So I instead just plan from 0 to the target, and by the way, the target is here. It needs to be normalized angle, which is achieved by passing it through a tan 2 function, which normalizes the angle between -p and p. And then I just when I read out the trajectory, I then also add the starting angle. So I saved the starting angle for yaw, and this just makes it possible to use this to use the same profile planning function for the angle, which can otherwise wrap around. But in this case, I just easily prevent that problem by just planning around 0 point instead of planning for the like, for example, you could have an angle that starts at like minus 3 and then going to 3, right? And it's going to move through this point where it goes from minus pi to pi and then down to 3 again. And if I plan from 0, I avoid that problem. And then let's see here. And then I have this controller stuff here. Let's see. Yeah, and here I add the profile calculated yaw set point to the starting point, and then I normalize this angle so I get the target yaw, and then I set the controller target to these values. Let's see. So actually it would kind of make sense to separate this. I removed the manual control mix in, and instead I just make it so that if the joystick is moved during the automatic move phase, then the controller goes automatically into manual mode, so the move is aborted. And let's see. So we calculate the errors, and then we have to filter the error. But I want to do it a little bit better this time. I want to filter the actual raw values. So let's see here. So for the yaw, I don't actually need to filter the raw yaw position because it's already very exact. But for the pitch, I do need to filter. And this is how a filter can be designed easily using MATLAB. So just calculate the values for the A and B coefficients for the filter. And this can be done using the butter or like any kind of filter function that outputs coefficients in MATLAB. I can then just specify the cutoff frequency and design this discrete filter that runs at 1000 Hertz. I can also then just easily check the response time and the step response of the filter directly in MATLAB. I could obviously calculate these values also dynamically based on the cutoff frequency, but I find it like it's completely unnecessary because these are basically always constant. I designed the filter when looking at the test data, and then afterwards I rarely need to adjust these coefficients because it just keeps working regardless of how much the actuator moves yeah. So this can be kept fairly constant. But the only thing I want to do here is I want to use the filter structure, I think, because I want to move this code out. So I'm going to do like this. See if I can do like this. So the idea is that I could be that I could just sort of print out the coefficients and just paste them into the filter configuration. So this is how I design this kind of filter. I generate the filter using the Butterworth filter. It's going to be a second order filter to kind of get a little bit better cutoff frequency, or rather the slope of the cutoff. And then I design it in continuous time, so I can set the frequency here in radians, and then I convert this to discrete time with the dt that is my loop time for the controller, and I extract the coefficients for nominator and denominator. And these coefficients for the discrete time transfer function are exactly the values that I can just use directly in the C code. So I get this kind of configuration here. So I'm gonna just I'm just gonna redo this part. So this will be struct filter config. I should be able to just do it like this. We'll see. We'll see if C language allows me to do this. Let's see. So you can see here, this is the discrete time transfer function, and the coefficients are directly the values for the nominator denominator. The B values are for the previous inputs, and the A values are for previous outputs. And then you just solve this for the let's see. Yeah, so it basically becomes because this is like let's see here, 65. Yeah. So this becomes input over output, and then you solve for the So you can imagine that there is a 1 here, so it becomes 1 plus 0.065, and then you just solve for this 1, which becomes your current output. Yeah, exactly. Actually, it's actually this one. So z to the power of 2. This is the actual output, which you solve for by just sort of rearranging this equation. But without this is not actually interpreted as a division. Instead, instead you just look at the equation for the inputs and for the outputs, and then you solve for the current output. Let's see. So I'm going to be using the pitch velocity filter, which is going to have the cutoff frequency set to 40 radians per second. Actually, I'm going to check this. I think it's radians per second, but I still always want to double check with Octave, because it's not always the same units. In radians, right? So or is this actually radians? Let's see here. So here they do 50 divided by SF2, and SF2 is 400. Okay. So this actually becomes pi times the cutoff frequency. Let's double check this, just to make sure. Use the Bode plot. Like this. Let's see. Ten, 20, 30, 40. Yeah, so this looks like the cutoff frequency. And then because it's a discrete time filter, it goes like this. It goes to infinite attenuation at a certain sample rate. Yeah, this seems to be 40 radians per second. Right. So if we let's actually make this a little bit easier to understand. Let's try to design this for frequency in hertz. So if this were frequency in hertz, this would be 40 divided by 2 pi. Is this correct? Would it be 6 hertz now? Yeah. Let's make this 10 hertz. And this could be this could be 50 hertz. Let's see. So because the pitch signal is much less noisy signal than the pitch velocity, and this is also I'm going to use the same filter for the pitch error as well. But because the pitch itself is much smoother signal, I want to use as high cutoff frequency as possible. In order to avoid any kind of delay, because if I lower the cutoff frequency, I also get a higher delay on the filter, so it becomes harder to control. So I want to filter out as much as possible while at the same time keeping the delay low. And the purpose of filtering the pitch itself is to get a better estimate of the derivative of the pitch. Or the error in this case, because it's the same values used. Let's see. So let's try this filter out. Let's see. I'm missing something here. Why is this complaining? Yeah, and by the way, you should never use static like this. This is just because I was just testing this code. This is actually very, very severe error in programming if you use static like this in the middle of the function. Yeah, basically I'm going to copy this calculation here. So basically what I'm doing here is just making the calculation for the output based on this transfer function, where I use the B coefficients for the previous inputs and the A coefficients for previous outputs. And then I just have to update this chain of inputs and outputs so that I shift them by one, which ends up just being like this. So self in, let's see, so in zero becomes the previous input, and self out 1 becomes self out 0, and self out 0 becomes the output, and then we just return the output. I'm pretty sure I would have to have this as a pointer, but I still want to try to compile this. Let's see what error I get from GCC. then controller will also have I'll call it the error filter. Okay, so that seems to work, and I think the syntax highlighting was just a glitch, probably. Like, why does this complain? This is totally a glitch. Yeah. Okay, so now we can remove this. And for the yaw, I just normalize the angle for the error. And for now, I'm not going to be filtering the error. Let's see. And then I have the PID controller. Yeah. So the way I design the PID controller is by basically implementing the PID plus feed forward, and the feed forward values can be easily read out by simply exciting the system and measuring the outputs, and then looking at the DC gain of the resulting system. I can show how to do that as well. Let's see. And the controller output limit set to between -1 and 1. And for the actual controller design, what I do is I just record the motion. So I have a script here that just records the output of the application on the STM32. And what I can do then is I can run a test here. Let's see if I can get this. First need to check something happened in the firmware. Oh, actually, I know what happened. It failed to verify because I have to power off the motors for it to verify. I think this has something to do with ST-Link reception of data. Maybe it doesn't use some pull-up resistor. Maybe it's missing some pull-up resistor. So verification phase actually fails. Writing to the flash works, but then just finishing it off and restarting the chip doesn't work because there's some problem with ST-Link reading out the flash when the motors are running, or when the PWM is running on the motors, even though the potential is set to like just 50% duty cycle. So let's see. Now it's running. And then I can power on the motors. And let's see here. So what I'll do is just excite this system using the joystick, and this is going to be without running the controller. This is just going to be open loop excitation of the system, and I'll record the data here. So I'm going to do. I'm going to start this run test, and then I'm just going to excite the system. So let's see. What is this? This is something is weird here with the maximum velocity. I think I messed something up here with the maximum velocity. So I have to go back to the code and check this. Actually, let's see like this. So I'll just connect here and FB measured. Why is okay, right. Right. Let's see. Let's see, pitch, speed. Could I be using this in some way that I haven't thought about? Because previously I was just scaling it between 0 and 1, but I kind of want to scale it directly. So let's actually here. Yes, this is wrong. Yeah, so I have to update this constraining as well. This is actually going to be so for manual control, yeah, this will actually need to be divided then by FB. Okay. So like this. So because this needs to be converted to the duty cycle now, and then I have to divide this by FB pitch max now. Duty cycle equals to, or duty cycle is and velocity are two proportional quantities. Yaw speed as well would be yaw max. I think this was the only change that I had to update. Okay, let's see if we can get some data recorded. Run test. And starting the motors. And then let's see. Yeah, now it's working much better. So let's see here. So I'm going to be just exciting both motors using the joystick. I just move the joystick in a square pattern. Okay, that's it, and stopping this, and then I can run show data script, which will show me what this looks like. All right. So this is what our current data looks like. There's going to be some display issues with the yaw. I'm going to fix them later. What we want to look at is the pitch. Let's see. Yeah. So this is the behavior of the pitch control. When the joystick goes between -1 and 1, the pitch motor starts moving. This is the velocity of the pitch motor, and this is the current of the pitch motor. Because we're not controlling the current at the moment, the current can actually go higher, but for now we're just concerned about positioning of this motor. So what we need to do here is make an estimate of the transfer function of this system from the joystick input to the actual velocity that we get when we measure the velocity of the motor. To do that, I can use my other script called model ID, or actually it's called ID models, and then it calls model identification MATLAB script. And this gives me, so let's see here, I have to update the script. Let's see. So I'm going to open this model ID script, and I'm going to remove this step because I want to have a look at the plot. So what I'm doing here is reading in the data. First of all, this is the data that is output as a CSV file from the embedded system. And this data contains a bunch of measured values. All of them are output as integers. What we are interested in this case, is the pitch duty cycle and the pitch velocity. And I feed this into the MOIN4 model identification algorithm with a sample time of 1000 Hertz. And this function finds a system that matches, or that maps the inputs to the outputs. And what I get here is the system for the pitch and the yaw. But then it's also possible to just iteratively identify the first order system, which is what I do here. This is basically a transfer function approximation, which is very easy to do when you have the measured data. You could just do like this. Let's see. So if we set, for example, in this transfer function, the first parameter here, this is the DC gain of this transfer function. This is a first order transfer function, and this parameter is the time constant. So this is how many seconds it's going to take for the, like if you do a step response, the 0.02 is how many seconds it's going to take for the output signal to reach 63% of the input signal. And the 63% is calculated based on natural logarithm. There is a formula for it. I don't remember it in my head. But the 63% is basically the level which coincides with the time constant of the system. And we can easily approximate this. For example, if we start with, let's say we start with time constant of 1 and the gain of 1. And then we just convert this function to a discrete function and simulate this with our discrete input data, which is in this case the yaw duty cycle. We can make this pitch duty cycle. And the time is also the time which is from the sample data. It is important to resample the data into constant sample rate, which I do in my loader script here. and I also calculate the pitch velocity and the yaw velocity using filters. And actually, I should be using the zero phase filtering field function, but that's for we don't need that for now. So in the model ID here, let's run this with a transfer function which just has unit gain and 1 second time constant. So we can make it more readable like this. So when we simulate this, we're actually simulating the duty cycle input, and we're trying to convert that. We're trying to map that into the velocity of the motor. So the duty cycle is the voltage. The duty cycle translates into the voltage on the windings of the motor, and the voltage translates to the velocity of the motor. You could look at it like if you have a wheel, like a water wheel, where you have water falling on the wheel. So the voltage is the potential. So if you make this waterfall, if you make the waterfall from a higher altitude, then the wheel will rotate faster because there will be more force coming down on the wheel as the water gains velocity. So that's how voltage works, and the current, like how much water is actually falling on the wheel, is going to control the torque on the wheel, so the force that actually rotates the wheel. So current translates into torque, and voltage translates into velocity. And when designing the controllers, it's important to know what quantity should you measure. What quantity is it that directly translates into the quantity that you're trying to control? So in this case, we're trying to control the velocity, so we need to measure, we need to know the voltage on the windings. And in this case, we can actually assume the voltage to be proportional to the duty cycle times the DC line voltage of the motor. But because the DC line voltage, for the most part, doesn't rise above the DC voltage level, if we're kind of operating within limits, we can just use the duty cycle. So if we plot this, so this is basically how to do the quick approximation without using any model identification. So we can do this by just repeatedly plotting this function. Let's see, ID models. So and if we just use the unit gain and unit time constant, we get the simulated velocity of the motor ends up being this. And this is not correct. So what we want to do here is set the proper gain here. And the gain is basically the DC gain of the system. We can directly read this out from the system identification. The problem is that with system identification, we get a slightly more complex function, which has the complexity we don't actually need for controller design. So therefore, I just read out this pitch, the pitch feed-forward constant, or the DC gain, and I have to calculate the gain for the transfer function by simply doing 1 over 0.18603. So I have to take the inverse of this value. So let's see here. 0.18603, and we get 5.37. Let's see, is this actually correct? Or is that only for the C code? Let's see. Actually, I think in here I probably can just use like this. 603. Let's see. What result does this produce? Yeah. So I was correct there. I have to do the 1 over. So let's make this -6. Let's see what result we get. So with -6, I'm actually getting this. This is quite weird. So basically, we have two large time constants. I'm going to reduce the time constant, and I'm going to see what I get here. Right. Okay. Let's see here. I have to also plot the correct quantity here. Pitch. And ID models. And this needs to be. This actually does need to be the raw value, not the 1 over. So 0.18603 DC gain. And now we can get, I think, a much better model. Yeah. So now we can do like this. So if I do the simulation from the input voltage to the velocity of the motor, I'm getting pretty close to the true velocity, which is this one. And actually, I'm going to update my loader script so that I don't use, so I can eliminate all of the phase shift from the signal. So for the pitch velocity, I'm going to use filter. And this will be, let's see, I'm going to use the same filter here. Same cutoff frequency, 10 times 2 times pi. And then let's see if we get a better true value. Yeah, so now I got rid of some of that phase shift. So I can make a better comparison between the transfer function and the actual measured data. So this is getting pretty close, and I could adjust the DC gain to kind of get this function to match the measured value better. So in this case, we can make it a little bit lower. Because remember, when we do the system identification on some measured data, it's not going to be precise. We still have to validate the system that we have identified. So even the DC gain value is not precise. So we can make this maybe -18. Let's see how this works. And actually, I think this one is slightly offset. Yeah. So I think this was actually pretty correct. It's just that the value that is output here is slightly offset. So if we do this -0.02 and check this again, and it matches a lot better now on the top side, but not on the bottom. Let's see. Actually, this kind of thing shouldn't be done. Let's see what this looks like. Now it's a little bit too low, so you can make it a little bit higher. I think this is a pretty good match. So this is the approximation of the system, and using this approximation we can then design the PID controller. Let's try to simulate the actual SUS pitch. See what result we get. This is the simulation of the identified system, and you can see it's not perfect. It's actually worse than the function that I've arrived at iteratively. It's worse than the first order function, which I've simplified here. So using this for controller wouldn't provide as good results. So now I can take this transfer function, the transfer function g, and I can use the feedback method and the PID method in MATLAB to create a transfer function for the combination of the controller and the motor. So if we use the PID values here, let's see. Let's do a little test just for the sake of the video, and use the PID value of actually just setting Kp to 2 and Ki to 0 and Kd to 0. And the feed-forward value here ends up being the DC gain value, which I got from the model identification. But 1 divided by that value. So in this case, 1 divided by 0.17. So it's like 588. And this will be the feed-forward value for the commanded velocity. So we can use this feed-forward value to get the base point of the control signal, and to ensure that the controller doesn't need to work very hard to stabilize the position of this actuator if we use the feed-forward. So let's see what let's just see what result we get here, or what result we should expect with this game. So I do a step, and I don't plot that one. I just plot this one. Let's see. So this should produce a pretty good result. However, it's not going to have very fast response time. Let's make it do something stupid. Let's make it like this. I think this should create an overshoot. Yeah. So this will create a controller that just overshoots way too much. I wonder if it's actually going to behave this way. Let's try this out. Time to record some data. And it is actually quite. It kind of gets. Let's see. Now I'm going to move it to the program position. Yeah. I don't think this wasn't too bad, but it's still like I can hear it clicking. So this D value is way too much, and the simulation shows that it's too much. Let's have a look at what this looks like. So this is the green is pitch target, the red is the actual pitch, and the black is the set point error times 1000. Or maybe it's 100, but it's error nonetheless. So we're getting kind of weird behavior here, especially looking at the current. It's just going up and down. So it's quite weird. And it will kind of never behave exactly as the model in the real world, but the model can give us kind of like a good feel for what is reasonable for this system. And setting the D value to 4 is way too much. 0.2 is more reasonable, and I'm using 18 as the KP value, which I've arrived at based on kind of a little bit of experimentation, and also looking at the produced plot here. Let's see, I just want to check something. I want to check what we get if we have this. And I think the overshoot can be identified by having a 0. Let's see. No, not show data. I do models. Okay. The input data isn't good enough here because I've been using the latest move as the input data. I'm going to delete the latest move, and I'm going to use the. I have to use the. Let's see here. Maybe this works better. Yeah, this one passes. Okay. I need to cut this one out. So this is what this one looks like. And I can't really see I think that one is a red dot. It's very hard to see the markers. I cannot see any markers here. That one looks like a green dot. Yeah. Let's see what it looks like when it's more reasonable. Maybe I can use the PZ map instead. I'm going to convert this into continuous time. I want to get the actual values for the dots here. Okay, so all the poles and zeros are negative here, and let's check the one that was suboptimal, which had 2 and 4. Get here. And this, yeah. This didn't look that different. I need to read up on this function, the root locus thing. Because this one clearly looks different. So maybe there is some explanation to why the control controller is suboptimal based on the looks of this root locus. This one. So anyway, the values that I've arrived at using the simulation here is 18.0.2, and putting them here also produces pretty good results. It gets rid of all of the clicking and jittering on the actuator. Let's see. Okay, so we're going to move from this position into the program position, and I'm going to record the data. And I'll see what the data looks like. Here we go. So looking much better. It's following the profile pretty closely. This is the error. Let me just check what scaling I have on the error. So check data here. Currently I have a scaling of 100. I could rescale this into millimeters. Let's see, so I'm going to check how long this actuator is. So once it reaches the end point, it actually starts rotating, which is good, because it prevents it from getting stuck. But unfortunately, if it hits something, it doesn't stay in one place. So this is around 23. Let's see. So I think it goes somewhere here. It's 20 centimeters. That looks reasonable. So so basically, it's very easy to convert this to millimeters. We have a travel of -1 to 1, and that range is 20 centimeters. So if we do like this, and then we have times 0. So let's say it's 200. Then one is yeah. Actually, this should give us the millimeters. This should be the millimeters. So this actuator is moving within 1 millimeter precision, and for a large portion of the move, it's less than 0.5 millimeters from the set point, which is good enough for this application. It may not be good enough for another application, but for this application it's okay. And the control signal is looking pretty good, and it looks like the controller is doing a pretty decent job at controlling this actuator. And in this particular case, I don't like to use the integral, because the integral would give me an overshoot. So I set the integral to 0, and I instead use a higher Kp value to get better response to any errors. And I also use the feed-forward value to get instant response from the controlled system. So I did a similar thing for the yaw here, and next I will just move this code around, remove the hard-coded values here. The filters can be hard-coded at the moment. I don't think I'm not going to be changing these values, but the KP, KI, KD feed-forwards, this would be better to place in the configuration, which can then be saved to the EEPROM on the board. Also, I really want to get the current control working, so let's have a look at the current. If I open the model, let's see, open the model ID, and let's have a look. I'm going to delete that file, and I'm going to check if I get this manually controlled data. Is this the manual data? Yeah, this looks like the manual data. So I could use this for model identification, and this time I will identify the current. And then instead of the duty cycle, I'm going to use the current. And this will be the pitch acceleration. And now we have actually we could call this pitch acceleration. And I'm going to add the pitch acceleration here. So I could calculate the pitch acceleration from pitch velocity and filter it as well. So pitch acceleration will be the filtered version of gradient of pitch velocity. Gradient basically gives me the derivative as calculated from the data, but then I have to filter it as well. And this is divided by the sample rate. That is dt. Could calculate the dt from the. Actually, no. I'll set the static dt because it's gonna give me better results in this case. And for the filter, I will use a slightly faster filter. So I could use the. Let's see. Let's start with 10 Hz. see what we get. I'm going to check the data first. So pitch velocity, and pitch acceleration. I'll make this light blue, and pitch. So let's have a look. This is quite noisy, so I need a bit more filtering. To get a better acceleration, let's see what filtering we can use. I could actually use a slower filter because because I'm using filter, I can actually use a much slower filter and still get good results without any delay. This is not really producing very good results. Not yet. Let's see. Let's see what results I get if I use the delay filter. Slightly better, but still very noisy. Yeah, this is way too noisy. What could this be? This could be like, what frequency could this be? Let's try so pitch itself can actually have a very low cutoff frequency. Right. I wasn't actually using that pitch either, so I've been using the normal pitch here. So this could explain why I was getting worse results than I expected. This is much smoother. This is almost too much filtering. And a bit too little filtering. Still looks a bit weird. Still looks like it's too much noise. The set point error is set to, like, the set point is set to 0, so that's why I get a big error there. The controller output is set to 0 as well. This is just the pitch that's moving up and down. Okay, so instead of looking at acceleration, let's have a look at the relationship between, or actually, I think acceleration would be very nice to get working, but I think it's way too noisy. Let's have a look at the relationship between voltage and current. If we can get something going there. Because we're going to be controlling the current by adjusting the voltage, which in turn will vary the acceleration, but we're still going to be controlling the voltage. So I'll set the from pitch duty to pitch. This is what I get so far. This is the current, this is the simulated current. Maybe I'll have to just do this by trial and error. What I do want to get though is the what if it's the feed forward value? That's of interest. Yeah, I would very much like to get some kind of estimate on the feed forward value from the acceleration to the desired current. which would be given by this, from the acceleration to current. But the problem is that acceleration is so... well, maybe this gives a reasonable value anyway. Let's have a look. So could this be... so 1 divided by 5, could that be the feed-forward value for the current? Based on acceleration. Let's have a look. Let's see how fast it's actually accelerating here. I can take this portion here. So it goes from like it goes from 0.2 units to minus 0.2, slightly less than 0.2 though. Let's see. Minus 0.16. And this one is 0.16. Yeah. So, and it does this in 5.5 to around 6. 5.5 to 7. Yeah. If we move this curve a little bit to the right, then it will be 7. So 1.5 seconds. Let's have a look here. So we go from so 0.16 times so 0.32 then. 0.32 divided by 1.5. 0.21 per second. What is the current? When it's accelerating, it's going to more like let's see. .4. This looks wrong. This looks very wrong. This almost looks like there is some discrepancy between the data. Because it should be getting more current when it's actually changing velocity, rather than when it's running at constant velocity. What is going on here? Maybe I have these values swapped or something. this is quite weird values, because this looks like it's moving already here. So what did I do wrong here? What is the issue here? I'm pretty sure it looked different before. Like, right now it's not looking very good. The current is not supposed to suddenly change here. Like, there's no reason for the current to change. It does look, however, that the joystick and the velocity are kind of aligned. Like, when the joystick gets over here, actually this one is not aligned either. Almost looks like there's some kind of delay in communication for the current values. I'm going to record some data. This is where I move the joystick a little bit. But let's see. So what the hell is this? This does look a bit weird, actually. It looks like the current readings are a bit off. Let's see here. Maybe there was something wrong with like the DC offset calibration or something. So it looks like, let's see. Weird. This is something that I need to debug. I'm getting, I think I'm getting some weird values, and it could be because something is off now in the sampling. It could actually have something to do with with the fact that I've adjusted the repetition counter for the timer. So maybe something went off there. This is something I need to have a look at. I'm going to connect my console to the drive instead of having it connected to the control panel. Okay. Now we're connected to the drive. And now, let's see. This will give a slightly different output, which will output, let's see. So this outputs all of the currents. Okay. So we get pitch, yaw, and we get the and this should actually be remote. It doesn't matter. Let's have a look at the currents. Let's see what we get. So the first value is actually the position, I think. Let's see. That'll be the pitch and yaw position. And then, actually, let's see. This will actually be the commanded output, and then we have the currents. So the pitch is currently measuring at minus 0.1. I think this is due to the joystick. Definitely need to calibrate the joystick. This is really weird. So sometimes, right, it seems to be that sometimes the values are correct, sometimes not. And I know why that is. I know why this kind of shit is happening. Because I have updated my repetition counter on timer 8. And I set it to an even value, which means that sometimes it's going to measure on the high edge and sometimes on the low edge because it's triggered by the update counter, or rather by the update event. So this has to be set to something that is not an even value, but rather an odd value, which will make it measure on the same. So before I had it set to 1, and that worked. So let's set it to 9, and set it on the other counter to 9 as well, and see if we get better results. So basically 0 means there is no repetition counter. It's going to fire on every single event, so both the high and the low. 1 means that it's going to fire on every second event, which would be, if it starts on high, then it will fire on the low event. So it will only fire on low events. And setting it higher will just make the update event fire at a much lower frequency. So let's have a look now if this gives better results. Yeah, this definitely has better results. But for some reason I'm getting, let's see, increase there is some weirdness going on here. Let's see, why is this so weird? So now all of a sudden my joysticks are switched. Let's set it to 1. At least the current sensing is actually working. I have to debug my joystick. So actually, I think this is interesting. So FB measurements. So now all of this stuff is off. Let's see if let's see. This is going to be raw values. Flash this one. Let's see what the joystick gives us. Minus 0. Yeah. So this seems to work, but is it not? Is there a fault of some sort? Or what? This is very weird. Because this looks like this is supposed to only run if we're running in master mode. Let's see. Mode equals. Okay. just do that once before doing the initialization or checking here. So that will update the mode based on the canvas. I wonder if I'm using the wrong output method. Let's see. I'm going to print out the output and see what I get actually on the output. Minus 500, 500. Interesting. What is going on? Why is it not working? Maybe it's actually, maybe it's slightly got disconnected. I don't know. I'm gonna check the actual output. There's quite a weird behavior on the outputs. Which I can see by looking at the scope. It's not actually being written properly. I don't know what's going on here. I'll check. Maybe I changed something in the output. Oh, god damn it. Oh, how could I do something this stupid? So in the function that was actually writing out to the motors, I made this update where I moved the constraining, I think, to a different place, and I did a copy paste here. So I was actually outputting pitch on the pitch model. That was weird. So outputting yaw on the pitch model. So let's see. Let's flash this and see if this works better. So this code only runs on the driver board and not on the master board. So that's why I didn't notice that I had this fault. Let's see. Yeah, now it's working. Okay, cool. So I'm going to reconnect to the... actually, I'm going to check first if I get the proper current readings. So FB data, and looking at the current readings now. Pitch looks good. Looks good. Yaw looks good. Yeah, awesome. So now I can actually go back to the control panel and work on the current readings. So the problem was that I had the even number of repetition counts when I had to have an odd number. Setting that number back to an odd number fixed the issue. Let's see. Okay. Did the terminal just hang? Or is it something else? Yeah. Looks like it's not receiving anything. Yep, better now. Alright, let's record some data. I'm going to exit Picocom and I'm going to run the recorder again. So run test, and this will, let's see, let's record some joystick data. Let's see, I have to restart the motors, damn it. I forgot to restart the motors because I rebooted the board, so I have to restart the motors. Okay, run test, and let's do this. Okay, that should be enough. And now I should be able to show this data, and it should look more reasonable than my previous data. this is because the first line in the file is corrupted. So I'm going to just delete that line. This can happen because I'm recording from the terminal. So let's have a look here. This is the file here. I'll delete that first line, and now I should be able to plug the data. Yeah, so this looks much better. This is more like the current readings that I would expect. So now it's the next step is to kind of try to map this. Let's see if the mapping actually works now. So I have let's see. Yeah, I should be able to just run this ID models. .26, and this is what the current mapping looks like, and it's minus 210. So let's update this to minus 210. See if we get a better result. So this will be the gain 2.1, and let's check this model. I'm actually simulating cis pitch, which is incorrect. I should be simulating the G model. I could try to simulate cis pitch I for the current model, the identified model. So this will be the identified model. This is fed with a duty cycle, and it's supposed to kind of like predict the current. And this doesn't produce very good results. So let's see. Yeah, this didn't produce very good results. It didn't even produce proper identification results. So let's try the G function, the one that I'm manually trying to identify now. What's up with this? Where is this failing? PZ. Oh, I think it's actually failing on the controller. So we have the. It's probably failing in the. It's failing in the D2C at line 70, line 29. Let's see. Yeah, it's failing in the PZ9. So it doesn't matter. But 126 is the value that I get here. Let's try this. No, this is actually wrong. So this needs to be identified from the duty cycle, because we're feeding the duty cycle here. So it has to be duty cycle there as well. Let's see what we get now. Now we get minus 210, and now I can update this value here. So minus 2.1. Okay, so I get something that looks like this, and this is not the type of response I would expect here, maybe I can get a better result with the second order function here. Let's try to do a second order function. And then I'll simulate the actual system that's been identified here. So going from duty to the current. Let's see if we get something that looks more like the current. Yeah. Okay. I'll go back to the so just to show what this looks like. This didn't really work very well. This looks like this. It's not following the current. So let's try to get some. I would need to use the acceleration actually, because I would need to calculate the feed-forward value for the acceleration, because current is proportional to acceleration. Acceleration and current are related, and because I'm going to be getting the acceleration set point, I can use the set point as a feed-forward value for the controller, for the current controller. But in terms of just getting something here when controlling the duty cycle, I think I'll just manually set this to something like 1.4. Let's try this. Just G here. I'm going to actually set this to 0.5. That should give a good voltage feed forward. 0.5. Okay. And the time constant can be set to something lower. Or actually, I could keep it that way. So now, when I'm going to be controlling the current, I'm also going to be removing this artificial ramp that I'm currently using in order to limit the current. So I'm using this ramp, which is defined in this fastest, output constraint fastest. This actually puts an artificial ramp on the voltage that is going out to the motor. And when I'm going to be controlling the current, I'm going to actually remove this, because I'm going to be controlling the current at a much higher frequency than the frequency of the control loop. And this ramp is not going to be necessary anymore. And this ramp is actually the reason why I'm getting this wrong. Let's see. So you can actually see the estimated slope of this curve. It's supposed to be much faster, because the current response is almost instantaneous. But when using this ramp, it's impossible to control the current with sufficient speed in order to be able to set it to a certain set point. So I'm gonna refactor this piece of code. I'm gonna remove this artificial ramp, and I'm gonna set up all the necessary variables for the current control. And then I'll come back to this in one of the next videos, maybe, if I have time. But for now, it's it's working alright without any current control, but current control would be very nice to have. Let's see. Okay, that's it for this video. Thanks for watching.